Log on, tune in, find out. Another good idea from Cambridge.
So, good morning. So, where did she put the stick? Okay. Good. So thanks to the organisers for the opportunity to give a talk. Very, very grateful for that. So what I was going to talk about is this topic of Bäcklund transformations for a discrete second Painlevé hierarchy. So what I mean by Bäcklund transformation there is actually auto-Bäcklund transformations. These are going to be Bäcklund transformations from a particular member of the hierarchy to itself, perhaps with some change in the parameters there. So not Bäcklund transformations in the sense of Pilar, where she was talking about Bäcklund transformation between different hierarchies or different equations. Okay, so this is what I want to talk about. So the contents of the talk. So just by way of a reminder and by way of motivation, really, go over things for the second Painlevé hierarchy. Then I'm going to define a discrete second Painlevé hierarchy. So the eagle-eyed amongst you will have noticed that there I say a discrete second Painlevé hierarchy, whereas here I say the discrete second Painlevé hierarchy. So the correct word should be a, because there's no reason why. Well, since there are several discrete second Painlevé equations, there's no reason why there shouldn't be several discrete second Painlevé hierarchies. So, for those who noticed these things. Then I'm going to talk about construction of auto-Bäcklund transformations for this hierarchy. And then a couple of further examples based on the same hierarchy, really. So the extensions of what I'm doing for the discrete second Painlevé hierarchy. So, but I'm going to talk about, just by way of example, one particular equation, which is a lattice equation, and an inverse, a non-autonomous inverse Volterra flow, really. But we obtain the same kind of Bäcklund transformation for this equation, and also for a differential delay equation. And then some conclusions. So really, talk is very straightforward, very simple. I just wanted to get some ideas across. So it's really some particular examples, and try to see some pattern underneath what we're doing that applies both to continuous and discrete equations, which is what we're trying to do, really. So the second Painlevé hierarchy. So the second Painlevé equation is, of course, the equation in y, which is written down there. Y double prime is 2y cubed plus xy plus lambda 1. So this equation is the second Painlevé equation. And this is a hierarchy of equations. So what we have actually is an equation for each even order. So the first one is of order 2, and then the next one is of order 4, and the next one of order 6, etc. So we have this quantity mn of w, and so this is a sequence of quantities defined by this recurrence relation, and these are the first few of those. So if we take the case m equals 1, for example, then this capital M, if we take alpha 1 to be 1, then this capital M is just w, so this just becomes yx minus y squared. So we see that we have d by dx plus 2y of yx minus y squared, which just gives this quantity y double x minus 2y cubed. So, and then the other terms give rise to these terms. So for those that recognize these things, this is obvious, well, which is everybody here, I would have thought. This is the Hamiltonian operator for the, or one of the Hamiltonian operators for the KdV hierarchy. This is the other one. And these m's are in fact the variational derivatives of the Hamiltonian densities for the KdV hierarchy. So, but as I say, I just wanted to really treat this in a very straightforward way. And so in some work, so in several papers, we've looked at deriving Otto-Bäcklund transformations for hierarchies. So the first work I had in this direction was in a paper with Nikolai Kudryashov, and then there was a paper with Peter Clarkson and Nalini Joshi, and then also a paper with Pilar and Nalini Joshi, which is where this is taken from. So what we wanted to do then, so then being some time ago, was to try to use the singularity analysis of these equations in order to motivate the transformation we needed in order to get the Bäcklund transformations. So that's where this comes from. So these were the formulas that we wrote down. So if you do what is called the WTC Painlevé analysis for, even though this is an ODE, if you do that for these ODEs, you find that these are the first two terms, and if you stop here, as a consequence of this choice, you find that this here, which is the mirror map, so I should have said yx minus y squared is just the mirror map between k dv and mk dv in y, that this mirror map is preserved. So preservation of the mirror map is a consequence of the choice you make here, because obviously you can nonlinearize this linear equation to get an equation for the quantity minus phi x over phi. And so what I'm saying is that equation, which is a Riccati equation, so it's the assumption of a Riccati equation, which gives the invariance of the mirror map. So what I want to do when we get on to discrete hierarchies is to do this the other way around and just say that we're going to ask for invariance of the mirror map, and as a consequence of that invariance we have a Riccati equation. I mean, so this is just very straightforward, but what it means is that for discrete hierarchies we don't need to, we can just use this straight away. We can just use this idea straight away. So I'm not saying that, obviously there are many papers where people use mirror maps to derive Otto-Bäcklund transformations, but I think that this particular way is something different. Excuse me. So this is what we're going to be looking at. So what I'm going to do is take a hierarchy, because I mean this is important because it's the quantity that appears here. So what we're going to do is take a hierarchy and assume we have invariance on the mirror map and use the consequent equation in the derivation of the Otto-Bäcklund transformation. So what is the discrete second Painlevé hierarchy? So Pilar has just written this down, or a discrete second Painlevé hierarchy. So this here is, no, this one here is our discrete second Painlevé hierarchy. So what Pilar just constructed is a Bäcklund transformation between, which is this pair of equations, the Bäcklund transformation, where this is the mirror map, and this is a Bäcklund transformation between this equation, which is a discrete second Painlevé hierarchy, and this one, which is a discrete P34 hierarchy. And the actual discrete second Painlevé hierarchy corresponds to a particular choice of this K. So in the same way as for the second Painlevé hierarchy, we have some quantities mj, and we have a recurrence relation between those, and these crop up in the definition of a hierarchy. So the same thing happens here. We have some quantities Lj and a recurrence relation between these Ljs. So where these B's are the Hamiltonian operators for the Volterra lattice. So this is Volterra example. So B and A are Hamiltonian operators for the Volterra lattice, and these are the first few L's. Okay, so the important thing in this structure is to have so this operator here. So this E inverse, so this is not E inverse of 1 minus q times k, this is E inverse of k times 1 minus q, if you see what I mean. So this operator acts on everything in front of it. So this is actually because this is the Frechet derivative of this is the adjoint of the Frechet derivative of the mirror map, so that we have sitting in here. So the important thing about this structure is that we have some operator acting on k, and then we have the definition of these k's in terms of L's, and these L's are defined recursively from this relation. So what we have in this way is a sequence of equations, again like in the continuous Painlevé 2 case, we have a sequence of equations of each even order. So for m equals 2 we obtain discrete P2, of course. And so the other thing of note is that we can, if we look carefully at this u, this quantity u here, and this operator here, so this operator here is cubic in the q's, and it turns out that it can be written as something in terms of something linear in the q's and u, which is quadratic in q's. So it turns out that this operator here can in fact be written in this way. There's a q minus 1 inverse of uk and a q n plus 1 of uk. And then we just relabel these constants so that they're relabeled according to the position in this hierarchy. So I think that's everything. Let me say it like this. So construction of auto Bäcklund transformations. So what I'm going to do is just look at the standard dp2 case. So because here in this equation, if this b2 is non-zero, then the continuum limit is p3. So what I'm going to do is look at the one that corresponds to p2. So I'm just going to look at the standard dp2 case, get rid of this b. So I'm going to take bm to be 0 in our hierarchy. So this is now our hierarchy. So this is a very nice way of writing it. As I say, linear in these q's, and where we have, so E is the shift operator as before. So we have E inverse, so we have Q minus 1 E inverse W plus Q plus 1 W minus AM. And what we want to do, where this W is just U times K, where K is defined in terms of these L's, evaluated at U is M of Q, so this M of Q is the mirror transformation. Okay. So what we do is we seek a transformation between our Q and the solution of a second copy of this hierarchy. So we're going to assume that Qn satisfies the same hierarchy for possibly different values of constants. And so if you ask that the mirror map is invariant, so if you ask that M of little q is the same as M of large q, you obtain this discrete equation. So this is the equation that is imposed by invariance of the mirror map. And then what we do is just a very simple calculation, in fact, because so we have our second hierarchy, this discrete equation. We have the result of substitution q is y plus large q in this equation, which is what I have here. And we basically use these equations to derive the Bäcklund transformation, because having assumed, or having shown, in fact, the reason it's so straightforward is because of this fact that our hierarchy can be written as something which is here linearing this q. So that means that when I substitute this mirror transformation in here to obtain this equation, what I get is something linear in y, which I can compare, and the linear part in q will cancel with the part that's with this discrete equation in q. So, so the fact that one of our assumptions in this integration process was that the corresponding equation was a linear equation for the modified variables in terms of the unmodified variables, has a resonance here in the fact that it means that we can definitely solve for this quantity y here. So y is just a minus c divided, so this is just the result of elimination between these two. Then what we do is we substitute in here this value of y in here, using once again the equation to be satisfied by capital Q, and we get that everything is compatible provided that a squared is c squared. So first case a equals c is just the identity because this y is 0, and then a equals minus c, should say, coming back to here, so in this result we can also replace E inverse of w from the original equation in capital Q. So from this equation we replace E inverse of w in here, and what we get is then this is the Bäcklund transformation. So we have Q is capital Q, and then this quantity, and this. So we haven't quite finished because we have to identify the transformations between their parameters. Well, it's not difficult to see that if we take, so we just use the definitions, this definition of W here in here, and it's not difficult to see that if we look for terms in NQ and constant terms, that these are the only terms that we have. So we make a simple change of variable to another constant here, another constant, additive constant, and the same in the second copy of our hierarchy, and this change of coordinate, this change of parameter a is minus c translates into am is beta m minus 1 minus cm, where now this is how our Bäcklund transformation reads. So this is a Bäcklund transformation for the entire hierarchy. So this is an auto Bäcklund transformation which maps between, so you take your hierarchy, you take the equation at any particular level, and this is a Bäcklund transformation from one copy of that equation to another copy of that equation with this identification of the parameters therein. If you want to see what kind of things you can use to generate solutions, so if you're interested in the process of generating solutions, there are two obvious seed solutions, which are that W should satisfy W of Q equals 0. So if W is 0, that means that this AM has to be 0, so capital AM is a half beta m minus 1. And then the other one is just Q equals 0. So if we put Q equals 0 in here, as I said, dots here are terms polynomial of degree at least 1 in Q and its shifts. So it's something that's 0 when Q is 0. So if this Q is 0, then we need to have AM is 0. So these are two possible C solutions. So for m equals 2, which is the first non-trivial case, we have this transparency has got absolutely nothing to do with me, in the sense that these are not my results. So this is just for m equals 2 we reduce back down to the known results. So we have two copies of the discrete second Painlevé equation, the auto Bäcklund transformation between them, and the equation W of Q is 0, which we can use to generate seed solutions, is one which is linearizable. We give this equation, so this is a discrete Riccati equation, linearized to get solutions from this equation, and we also have the solutions Q equals 0 for A2 equals 0. So these results are due to Romani and Grammaticos, of course. So what we've done is extend these to the hierarchy. So probably going to finish a bit early. So further examples. Well, so I got rid of the BM term. So if we leave this BM term in here, if I leave this term in here, then everything goes through in the same way, except that we obtain that we must. And so so leaving that in there means, of course, that in the two copies of my equation here, in this equation and this equation, I must have. So here I have minus bm minus 1 to the n. So I need to have a minus dm m minus 1 to the n here to have a second copy, but the only change is the inclusion of these parity terms in the denominator and identity between these two extra coefficients with the same shift in parameters. And so the second example is perhaps a little more interesting, the second of these further examples. One thing that should be noted is that in all this process, so in this construction of Bäcklund transformations here, what I've got here is the equation written in terms as linear in Q and in terms of this capital W, in terms of this W. And in the construction of these Bäcklund transformations, I don't at any stage actually use what W is. So this expression, so this is the expression for W which gives me the discrete P2 hierarchy. But in the calculation of the Bäcklund transformation, I don't use what that is. Which means that I can easily generate further examples from here. So again, the same is true for this example. So if I include this extra term in the calculation of the Bäcklund transformation, I don't use at any point what W actually is, which means that, which is the same as saying that I don't use what K is, K because W is just UK, and which means that here I can change K arbitrarily and I will still have a Bäcklund transformation. I'll still have an auto-Bäcklund transformation. So the first thing is to think about changing K in a way that the equation remains integrable. So if we change K in a way, so that's possible because what we can do is we can include these terms. So if we include this term, for example, so instead of W being just UK, we now got U. So we have this operator A, so we now have an A inverse. So we're going to allow U to depend not only on N, but on a continuous variable Y. So we have now an A inverse du dy plus K. So this actually corresponds to, so in the language of Pilar when she was talking about the unmodified hierarchy and the modified hierarchy in the integrations of each of these. So what this actually corresponds to is that in the unmodified hierarchy, we now have terms which are quite strange terms as far as I know. I mean, I don't think these terms have been written down before, which were things like we had the recursion operator for Volterra, acting on uy. So we had, so in our so slight change of notation. So this is this. So and then there's beta tilde. So I have everything I had previously in the unmodified hierarchy, except that I now include these terms. So this is like an inverse. This is like an inverse flow for Volterra. But I mean, what is strange is to see this recursion operator, which is a shift operator, acting on something with a derivative here. So, and I think that's something that was new when we published that kind of equation. And so, and this is, in fact, then in the usual sense, when you talk about KdV, etc., an inverse Volterra flow. And this thing here, with this choice of W, this equation corresponds to an integrated, summed, modified inverse Volterra flow, is what it is. But the important thing is that the same expression here gives me an auto-Bäcklund transformation of this form. for this lattice equation. And then we can also, in fact, allow n to be continuous, and instead of uy, consider a derivative with respect to that continuous variable. And if we do that, this then becomes a du dx, where so u and q are now functions of x. It's now du dx. So this is now a differential delay equation. So what we now have are shifts and derivatives with respect to the same continuous variable x. And this expression here gives us an Otto-Bäcklund transformation for that equation. So the other important thing then is, so as I said, so what I was saying was that at one point was that we can change this w, or this k, and one way we can do that is to keep the equation integrable, which is what we've done so far. So here we've kept the equation integrable, because we have lag space for these equations. So we've kept the equation integrable here. But the other way you can do that is to allow the equation to be non-integrable, and you can still derive a Bäcklund transformation. And which then means that we can derive this kind of Bäcklund transformation for non-integrable equations. Because as I said, all of this process only depends on this w here. So the important point is that this kind of Bäcklund transformation is not sufficient to be able to claim integrability. So whereas it's often claimed that there's a close connection between Bäcklund transformations for ODEs and their integrability, we can write down ODEs which have Bäcklund transformations, but which are non-integrable. So the conclusion, so as I say, so we've got Bäcklund transformations for each second Painlevé hierarchy, also for lattice and differential delay hierarchies. Existence of this kind of Bäcklund transformation is not sufficient to be able to claim integrability. And the general scheme that we're working on is this one, where so this is whether this is discrete or continuous, of course. So what we have is, so our equations look like this. So this can be matrix, of course. Omega is the solution of modified Hamiltonian acting on omega equals 0. And so we have m prime adjoint k of m of q plus omega equals 0 with this transformation to a second copy of the hierarchy, insisting on invariance of the mirror map. So this is actually, so this equation is a differential equation or a difference equation, depending on which case you're considering. So, so as I say, so we're looking at particular kinds of equation. Okay, so I'm not claiming a general method of constructing Bäcklund transformations. What I claim is that we have something general within a particular class of equations, and we have already several examples where we've done this. So apart from P2, we have a fourth Painlevé hierarchy, and we have these discrete examples, these lattice, differential delay, discrete second Painlevé. So this is the kind of thing that we're trying to get towards doing at the end. Okay, so sorry, I'll stop there.
Are there any questions?
I have a good question. When you have a non-integrable term, in what sense do you call the ODE Painlevé? I mean, does it have the Painlevé property? It's not clear to me.
I wouldn't call it. If I have, so you mean in here?
You have a non-integrable term.
If I allow this W to be such that the corresponding equation is non-integrable?
Yeah.
I mean, I wouldn't call it Painlevé
You
anyway.
wouldn't call it Painlevé because we don't know if it has the Painlevé
Yeah.
property. Right?
Yeah, I mean, I was just talking, yeah.
Yeah, it's a self-Bäcklund transformation.
Yeah, it's just a Bäcklund transformation between any two equations of this form.
Mm-hmm.
The same thing happens for P2 hierarchy, in fact. So if you have d plus 2y, and here some function of y and its derivatives plus constant equals 0, you can get the same result. You can get that for equations of that class, you can find Otto-Bäcklund transformations even when they don't correspond to members of this Painlevé hierarchy. Yeah.
Let's thank the speaker and all the speakers in this morning session.